Hey, this is Mr. Mitchell with a little bit of instruction about motion and speed, two terms that you have known about for a long time, but I kind of want to talk a little bit more about them and maybe expound upon it some. Motion and speed. Let's talk a little first about motion. Now, motion, we only know there's motion when you have changes against a background. For example, here we have this woman with a baby buggy. And if we move the woman forward with the baby buggy, we only really know it's going forward because of all the buildings staying still in the background. That defines its motion, not as much the actual movement, but the fact that other things are not moving. So what stays the same of any backdrop is called the frame of reference. Now, I do want to point out that you have more movement than just the woman with the baby buggy. You also have movement from the buildings because of the rotation of the earth. The buildings, everything on earth is moving. However, we don't have a frame of reference for that. As we look at the buildings do not appear to move because nothing around it appears to stay the same while it is moving. So we can't really define the building's movement because of the rotation of the earth as being motion. Motion has to have some kind of backdrop that is staying the same as something is moving. So that's kind of a notation about motion. Now, you know what speed is, and you can calculate speed, and that makes the motion measurable. So speed, of course, is the distance traveled in a certain time that it takes to make this distance. So if this lady with the baby buggy is moving, she may move 10 meters per second or something along those lines. And yes, the typically speed is calculated in meters per second. However, you know, when you get into something faster, you'll have miles per hour or kilometers per hour. So there's a term here called displacement. Sometimes you see the term displacement whenever you're referring to speed. And what is literally happening is this baby buggy is being displaced from one place to the next. So you can measure the displacement, you can measure the speed also. So that's a little bit about speed and motion. Distance over time is how you calculate speed, and we would like to be able to put this on a graph like this, called a distance time graph. Now, most distance time graphs have meters up one axis and have time in seconds along the other. So let's see what's happening here. I want to move some things around because my noggin is in the way, I believe. So here we have this distance time graph where we have a line, and at 10 meters, you have had 1 second take place. So just like this lady who is here, if you start the timer at 0 seconds, she is still, and 1 second later, she has moved 10 meters. That's how that would look on the distance time graph. So what happened in the second? You do not have any distance being traveled, but you have time passing. So this lady is just standing there. On a distance time graph, you have flat lines whenever there is no movement or no motion, but time is passing. So look what happened on the next second. You had a movement of advancement of 10 more meters because that is 20. The next second you had 10 more meters because it is 30. The next second you had 10 more meters because it is 40. So she is moving at a constant pace throughout all of this. However, look at this 5th second. She ended up being advanced 40 meters and then went back to 0 meters. So in that last second, she literally went 40 meters in the last second backwards to the beginning. So in grand total, she ended up not making any motion because motion needs to have a distance that you have traveled. So if you have speed equals distance over time, for 5 seconds, she actually traveled pretty good ways. Oh, I'm moving things around. So for 5, okay, so at 5 seconds, you had 40 meters for 5 seconds. So her average time is going to be 40 meters over 5 seconds, which is going to be 8 meters per second. However, what if you calculate the meters per second after 6 seconds? You would have, what would the distance be? The distance would be 0 meters. So 0 meters after 6 seconds is going to be 0 meters per second. So yes, her average speed after 6 seconds is going to be 0 meters, whereas after 5 seconds it's going to be 8 meters per second. So you can kind of see what is happening here. It is very hard for people to keep constant speed. If you're walking any sort of distance, you almost always sometimes walk a little faster and sometimes walk a little slower. So whenever you have calculations like speed equals distance over time, you are invariably going to have average speed, where the person starts out, where they end, and the time that it took to get there. Now, you probably figured out that I do want you to know a little bit about these time graphs. So I have these blank graphs, these blank distance time graphs, I should say. And I want to kind of point out what it looks like whenever you have certain things happen on these distance time graphs. Now you notice that we had something that was going kind of straight across earlier. If you have a higher angle on your distance time graph, you're probably going faster, or whatever speed you are calculating is going faster. But if you are not going as fast, it will be more of a flatter line, still going upward as far as going up this axis, which will be distance, but it's going a little bit flatter. Now I'm talking about distance is going to be on one axis and time is going to be on another, and that's going to be the same for all your distance time graphs. Now constant speed, I mentioned that constant speed is something that's really kind of hard to attain. If you have constant speed, you have a line which is just a really kind of a perfect line there, and I'm going to cheat a little bit. So you would have something like this that is just perfectly diagonal if you do have a distance time that is constant speed. And it's very hard to keep constant speed, because what's going to happen is you're going the same distance every single second. Every single second you're going the same distance, and that's just very hard to do. Now what happens if you're going backwards? If you're going backwards, you're not going a straight line, because if you're going a straight line like we had in the last slide, you can see you're just not moving. If you're going backwards, that's when the line starts going down. So going backwards is going to be in that section right there where the line is just going down. And I have this extra one right here just to kind of point out that in reality, if you were to actually make a distance time graph for somebody who is walking in the hall or walking somewhere, it's not going to be straight. You will have moments in which the person or object is going fast, and you'll have moments where the person or object is going slow. So you might have a little bit like this, a little bit like this. You will have variabilities in it. Maybe they're going to just stand still for a moment. But that's what it would look like in reality, and I hope to have you calculate some of those. Well, that's been a little bit about motion and speed. Hope you learned something. Bye-bye.